All right, so today we're going to finish up with trees and tree-based data structures. And then I'm going to devote Thursday to just a wrap-up and a retrospective on the entire course. Remember that we are online. If you have any questions, go ahead and post to Piazza. Otherwise, we left it off with I believe, we went through the basics of all three of these, right? Remind me? We showed how to search a binary search tree because of the binary search tree property. You start at the root, and if that's not what you're looking for, and what you're looking for is less, you go into the left subtree. And if it's greater, the thing that you're searching for is greater, then you go into the right subtree. Likewise, if you're going to insert something, you do the exact same thing. You search for where it should be. So, for example, suppose that I wanted to insert 55, right? Then I would do the exact same kind of search. 55 is greater, so I go right. 55 is less, so I go left. And so I find an open space here, and that's where I end up inserting it. I always insert as a new leaf in a regular old binary search tree, right? So this would end up being a left child of 60, right? Now, how did delete work? Well, first of all, again, you have to find the node that you're going to delete. And once you've found the node that you're going to delete, you have to replace it with something because you can't just, snip it out entirely. For example, if I wanted to delete 50 here, right? We've got both children here. If I just tried to promote one of these children, then I would end up having 1, 2, 3 children, and that's not a binary search tree. So to preserve the binary search tree property, what we have to do is we have to replace that element. Let me go ahead and go with white here. If I was to get rid of 50 at the root here, then what could I replace it with? The strategy that we developed last time was, well, let's go to the left subtree and look at all the elements over here, and whatever we put up here has to be greater than all these elements. So all we need to do is find the maximum element here, 49, and we can promote that up to the top. Right? That preserves the binary search tree property. Unfortunately, what do we do with that missing 49 now? We promote its, now we do cut ties, right? Now, we went over delete last time, right? Okay, good. Now we do cut ties here, and 48 moves up. The only time that that doesn't work is when you've got 2 children, because now which one of them do you promote up? That can't happen because if you were searching for the maximum value, then that means that there would that's not the maximum value. That it has a right child. Keep going to the right child. Go right child, right child, right child. After we developed all those ideas, we came over here and we started implementing them. And I believe that we did do the contains, the search version of this. We simply returned true or false on whether or not this binary search tree contained that needle. We did not get to the insert part. Instead, I did this offline. Nor did we get into any testing. Remember that I think I built like a 3-node tree really quickly to troubleshoot it. But ultimately, what I did here is I developed this tree. So let me go ahead and reverse all this. Right? This tree right here, I built all the tree nodes manually so that we could have something to play around with. Right? Let's go ahead and try to search for, say, 42. Let me go ahead and get rid of this. Over here, do we see 42 in this tree? Nope. What happens? 55, 42 would be greater than 40, less than 45, and we find that it's not here. So we would expect this to output false. And once it does, it does. Once it runs, it does. Let's search for something that we do know is there. 50. Right? We're going to get lucky here, and because it's right at the root, right? Or it's right at the top there. And when I run this, it should have said true, and it did. We can try some other corner cases here, or we can automate these tests like you will do in your lab tomorrow. We've already written a test suite using JUnit to test your implementation of your binary search tree. Okay. Now, I went ahead and, I think it was in the other section actually, went ahead and implemented the insert feature here, which I will go over line, we're not going to rewrite it because it's already here, but we're going to go over it line by line here. So if you're going to insert an element, of course, you need a new node to put that element in. One corner case is if you've got an empty tree. In other words, the root of this tree is null, in which case you are inserting into an initially empty tree, in which case you simply set this root to the new node, and that's it. You're done. Right? Otherwise, what I did is I implemented this other method called getParentOf. So again, let's understand how this works. First of all, if I want to insert, say, 60, right? I won't write that down because it's already in the tree. So what we would do is we would search for it first. So 50, then over here 60. Oh, it already exists. So should we go inserting it? Probably not, unless you want to really support duplicates, in which case you have to redesign it so that it goes left or right. Or you could just break ties arbitrarily. Right? In this case, though, we're not going to insert it. I've decided that this should be a no operation. In other words, I implemented this getParentOf, and if the parent returns false, the behavior of this is if the needle exists, we'll return null as a flag value to indicate that that key, that needle, is already in the haystack. In which case, I do nothing and return. Right? Otherwise, what I've done is I'm getting the parent of where it should be. Right? So let me go back over here, and we're going to insert 55. Okay? Where do I insert 55? I insert it as the left child of 60. What I actually need is the parent, because I need to make sure that the parent is referring to that child and that the child is referring to that parent. So all I've done is I've taken that functionality of searching for, I don't want to search for 55. I want to actually search for the parent of 55. And I've put that over here into this method, which is exactly the same method that we developed last time. It just has this other corner case, that if you find what you're looking for, instead of outputting true, right, or returning true, we'll return null because that key is already in here. That needle is already in the haystack. Don't insert it again. Otherwise, I've got the parent here. Now what do I need to do? Let's go ahead and visualize it over here. I've already created my node 55, right? I did that at the top. And I need to make the parent point to this new node. In this particular case, it's going to become a left child. But if I were inserting something, say, as the right child of 95, say 101, right? I would need to insert it as a right child. So I need to make that decision. I'm looking at the parent, and I'm getting its value. And if my value is less, then that means I need to be a right child. Sorry, if my value is, my parent's value is less than my value, I need to go to the right. Otherwise, I need to be the left child. So parent, set me as a right child or set me as a left child. Right? And that's all this if-else condition is doing here. Right? Now, I ended up not... Oh, I set the parent here because, of course, that requires no decisions at all. Right? I am simply making the parent refer back to my parent. Right? And then I return true. I'm using this return value here to indicate that inserting the node had an effect on the tree. Yes, I was able to successfully insert that. Or, no, it already exists. I'm not going to do that for you. Right? And if you choose to ignore that return value, so be it. Right? But if you want to use that return value, then you can use it to indicate that, yes, I successfully inserted something, or no, it was already in there. Right? We have enough time today before we talk about the last thing that I want to talk about, to potentially do the delete method if we want to. So public, I'll make it a void function for now, delete, and we'll take another element here. Right? Okay, so what's step one in deletion? Here, let me go ahead and reverse all this. So step one, I say that I want to delete, again, the example that I was using was 50. I want to delete 50. How? First of all, I've got to find it, right? So I'm going to find the tree node that contains that key. Tree node, T. Let's say node, I'll just call it node, is equal to, I need to find the node. all right, containing that element. Do I have that already? I've got an insert. I've got get parent of, okay. But that returns, again, if the needle already exists, it's not returning that, it's returning null. I've got contains, which returns true or false. So it looks like I probably need another method here, probably the exact same method as this one. Let me go ahead and cut and paste that. And I'll make it into a tree so that it's returning the tree node that contains this thing. So find node of that element. All right? Now, I copy pasted here. Should I make this into a public method? So it's giving you the tree node instead of the element. Should the outside world be able to call something like that? Probably not. It's leaking information about the internal workings of the tree. If I want to find that node and then I want to go mucking with its parents and its children, right? Then I'm doing that outside. Doing that inside the class is perfectly fine because it manages itself. Doing that outside of the class is not fine because it's leaking an abstraction, right? It's violating encapsulation. Okay, so I will return what? The current, right? Otherwise, go left, go right, and finally return null if you don't find it, right? I only changed 2 values there, right? Is there a way that I could probably refactor this code so I don't have too much, repeated code? Probably have this one call the other one. And then I want to return true or false depending on whether or not it exists. If it doesn't exist, I end up returning false. So return, does it contain it? Node, if it's not equal to null, then it contains it. If it does equal null, then it doesn't contain it. Right? So now I'm not violating the DRY principle, the do not repeat yourself principle, right? One function method is calling the other method. The public method is calling the private method, and now this private method has use beyond just what I'm doing here. In fact, I wouldn't be able to use it here because I need to keep track of a previous and a current, right? And the current could end up being null because I could fall off the end of the tree. But in any case, let's go down here to find the node. Find node of is what I called it, right? So I need to delete that node, okay? So I found what I'm looking for. I have found 50. How do I go about deleting it now? What if instead of 50, I wanted to delete 75? Find it. If there are no children, then what do I do? Exactly. So let's take some cases here. If the node dot has left child, they don't have their left child, and node does not have their right child, then what do I need to do? Just set my parent to null. It's left child or right child to null, right? And so now I do need to determine, am I a left child or am I a right child? I'm going to do that as a to-do. Right? If the node is a left child, then node dot get parent dot set left child to null. If the node is a right child, then node dot get parent dot set dot set right child to null. Okay. All right. How do I determine if I'm a left child or right child? If node dot get parent dot get the left child is equal to the node, then I do this. Oops. All right, do you see that chain of stuff? I'm the node. I'm getting my parent. I'm asking my parent, give me your left child. Is that me? Right? Otherwise, I must be the right child. Oops. There. Right. And this gives me an opportunity to talk about a classic poem or a brain teaser where a guy walks up to a painting and he says, I know this person. And he says, brothers and sisters, I have none, but this man's father is my father's son. Who am I? Who's in the picture? So, again, brothers and sisters, I have none. I'm an only child. But this man's father is my father's son. Therefore, I am, who's in the picture? Me. Or the man that was speaking there, right? So that's what we're basically doing here, right? We're asking, parent, are you the left? Am I the left child or am I the right child? Right? Brothers and sisters, I have none. But this man's father is my father's son. Before we go on to the other cases here, maybe we should have thought about a corner case. What's one corner case? Oh, if it's the root. But if the root has children, do we want to get rid of those children? Okay, so I'll have a to-do here. Just as a reminder, should we handle the root differently? Right. And we can come back to it. Always be thinking about those corner cases, though. Else if, how do I determine if I only have one child? This is if I have no children. Right. If I have one child, then I could have the left child, but not the right child. Or what? Or the other way around, right? Or node does not have the left child, and it does have the right child, right? And make sure that I've got brackets everywhere. Right. This means I only have one child. Then what should I do? Let's go ahead and visualize this. If I only have one child, what does it look like? I want to delete, say, 60. I promote 90 up to 60. Basically, I'm cutting these two ties just as if it were a 3-node linked list. Right. The problem here is, though, again, brothers and sisters, I have none. This man's father is my father's son. I have to determine, am I a left child or a right child, right? And then I can make the appropriate adjustments, right? If node is a left child, then ... I need to to do. I'll leave that as a to do. If the node is a right child, then ... What does it look like visually? Here it is, the right child. Here's the node. And so I need to take my node's father and set it to, now here I need, not only am I a left child or a right child, but is my only child a left child or a right child? So there are going to be a whole bunch of if, else, if statements here. Or you could probably simplify it in the end. I'll leave that as an exercise, though. But what you would do is you would get the parent. So 1, set the parent's left or right child to, actually, I am a right child, so set its right child to node's only child. Right? And 2, what else do I need to do? I need to set the node's, only child's node parent to parent, right? So I'll leave those as exercises because it's just a bunch of, you have to get it right, but it is a bunch of reference shuffles around, right? And a bunch of if, else, if conditions here. And at that point, you decide, well, I've got a lot of conditions here. Maybe I should revisit my node class, and maybe I should add some convenience methods in here. Am I a right child? Am I a left child? I already have has right child, has left child, right? Is leaf. maybe I should add something else in here. Public Boolean is a left child, or is left child, right? And how would I determine that? This dot, I'll get my parent, this dot parent, and dot get left child. If that's equal to me, right, then I return true. Or to simplify this, just return that expression. Right? How do I determine if I am a right child? Is exactly. And that would probably simplify a lot of this code over here, right? Should we get, and maybe you can also go with get number of children, right? Another convenience method, which would return 0, 1, or 2, right? How many children do I have, right? And put that into the tree node. That would greatly simplify things over here when you're working with the tree. Right? Always think about refactoring. Always thinking about, gee, I'd really like, I mean, this is, I need to determine if this node is a left child or a right child. I can do that externally from outside the node class, but gee, that sounds like something that is useful beyond just what I'm doing right here. I could use that in several places. And it's a function of the tree node. Where does it belong? In the tree node class. Encapsulation. Else if, and this is the one that I want to maybe fully do here, or not. Else if just an else here. There are 2 children. ... So now what do I do? 1, find the max of the left tree or the min of the right tree. All right? And then go back and either do this one or this one, depending on how many children it has to delete it. So maybe I probably want to refactor this a little bit and have a delete if 0 or if 0 or 1 child method, right? And then a delete method that calls that method, right? Lots of ways that you could do this. What I want to do, though, is just as a demonstration, let's go ahead and implement that find min or find max. So public, actually, I'll make it private first. Private tree node, T, find max. Right? Given a tree node, T, root, right? Because I don't always just want to find the maximum at the very top of the tree, the entire tree. I want to go down to the left subtree or to the right subtree and find the maximum or minimum values there, right? In particular, I'm going to go to the left subtree, and that's my new root, and that's my new smaller tree. And I want to find the maximum among all those. Right? So visually, what does that look like? If I'm going to delete 50, I go down to the left child, and then where do I go to find the maximum? Just keep going right, keep going right, keep going right. Right? You don't have to do an in-order, pre-order, or post-order traversal here because it's a binary search tree. Once you're here at this new root, just keep going right until you can go right no further. Right? So, current tree node T current is equal to, I'll start at the root, and then while the current is not null, I will go right. Go right. So current is equal to current dot get right child. Once I've fallen off the edge, right, then that loop stops. Does that give me what I want, though? What can I return at this point? I mean, I've got the root, but that was given to me. I've got current, but if I'm out of this loop, current is now null, right? Ah, okay. Return current dot parent. Yeah, it's going to be null, so what's going to happen? Null pointer exception, right? Well, within this loop, it's not null. So right child Is that okay? Good. What we could do, two options here. Well, the one that you were suggesting was kind of keep track of two things, right? Keep track of the previous and the current, and so you are always advancing that previous current, or previous current, previous current, previous current, and then previous current. Previous is what I actually want to return. That's one way. Another way, which I like even better, is what? Stop short, right? Don't go until your current is null. Keep going until the right child is null, right? So while current dot get right child is not null, go ahead and go to it. Right? But otherwise, stop short. Once current is 49 here, then you don't want to go any further. And I can return current. Exactly. you stop before you run up to the edge of the cliff and then you stop. The other way would have been that your buddy is tethered to you and they stopped. You fell off the cliff, but they pull you back up because you're tethered to each other or something.
Hey, I think you should have looked before you walk off the cliff.
Well, he was depending on you to save himself. He's fine, right? Now, because I have this and because I have this functionality here, of course I can use it, which I won't finish this out. To do finish, right? Tree node t find max, or max of left is equal to find max of, and then I want to go to the left child, so node dot get left child, right? Max of the left subtree, right? But I can also use this functionality publicly. Public t get max tree node t, and actually no, I don't have any input here. I will simply start at the root. So return find this dot find max of this dot root dot get value, or dot get value. Right? And because I already built this functionality in to do other things, I can use it up here to get the maximum, right, of the entire tree. What would that look like? Well, it starts at the root, keeps going right until you find what you're looking for, 95 here. Likewise, what would get min look like? Just keep going all the way left. Right? Both of those are going to be what? Order D, where D is the depth of your tree. Unfortunately, as we observed last time, 10, 20, 30, 100. The depth here could be order n. If you've got this very skewed binary search tree, it's essentially a linked list, and you're back at square one, right? Unfortunately, there are better solutions to this called balanced binary search trees. Balanced binary search trees work such that, and I think I previewed them last time. We won't get into them, but they rebalance themselves. So if you're too skewed to the right, well, what we're going to do is we're going to build a hill here, and we're going to have a guy pull it onto the other side of the hill, giving you 10, 20, and 30, right? And as long as you're always rebalancing the tree as you insert new elements and as you delete elements, because deleting elements could, lead to skewed left or right, all you need to do is rebalance it in some way. There are a couple of dozen implementations of a balanced binary search tree, but again, we don't go over that in this course. Instead, what I want to do is I want to show you another alternative called heaps, binary heaps. Right? And again, the motivation is that trees are not necessarily well balanced. There are trees out there that are called balanced binary search trees, AVL trees, 2-3 trees, red-black trees, et cetera, et cetera, et cetera. They work by rebalancing the node. An alternative is a heap. Right? So what is a heap? A heap is a binary tree that has the following properties. It is a full binary tree. Right? At every level, all nodes are present except for possibly the last deepest level, right? Which is full to the left. Right? Now, what do I mean by that? I mean that it has the following kind of shape. This is the general kind of shape. If it's full, then all the nodes are here. It could be that the last level is not full, but it's not going to have nodes hanging just wherever you want to put those nodes. Instead, all of the nodes at the last level are going to be full to the left. Oops. So it's going to look something like this. Right? That's the general shape. For a full example, let's go ahead and take a look at what I've got from the book. Come on. Where are you? There we go. Right. Now ignore the key values for a second. We haven't gotten to there yet. But you can see here that it is full. All of the nodes are there except for the last level. The last level has 2 nodes and they're all full all the way to the left. This would not be a heap. If I had a node hanging over here, then I've got a whole bunch of missing nodes between those, and that does not satisfy what is known as the fullness property. Right? This is called the fullness property. And the second property that a heap satisfies is that it satisfies the heap property. The key in any node is less than, that's for a min heap, or greater than, that is for a max heap, both of its children. Right. So let's take a look at this example here. Is the heap property satisfied? Look at the key in a node 1. It is less than both of its children 5 and 30. Look at another one, 55. It is less than both 72 and 70. Another one, 90. It has no children, so it doesn't matter. Right? 60 is less than both 92 and 63. Right? That's a min heap. Why should we call that a min heap? Where is the minimum element in this heap? It's at the root. What if it were a max heap? Max heap would just be an inversion of this idea. And we would have something that looks like this. We've got 77 at the top here. Tell me about 77. What value is that? That's the maximum. This is a max heap. Doesn't really matter. Min heap, max heap. Right? All you have to do is take your comparator and reverse it. Right? And you've turned a min heap into a max heap and vice versa. Okay? Now, we don't have a lot of time today to go over the implementation details, but what I do want to do is I want to make some observations about its structure, and we're going to develop some algorithms to exploit that structure. Okay? So my first observation is that in a max or min heap, the maximum or minimum element is always at the root. Right. Cool. And what's another observation here? Because of the fullness property, what can you say about the depth? The depth of a binary heap is D is order what? Remember, we started this all out by saying, here's a tree, and suppose that it's full, and it has n nodes. And then we derived an equivalence of, well, if you add them all up, you're adding up powers of 2. 1, 2, 4, 8, 16, ... Once you added those up, that was another power of 2. So if you reverse that and you look at the depth, then the depth is what with respect to the number of elements? Logarithmic. We didn't have that guarantee, as we just observed with this skewed example over here, right? We don't have that guarantee with binary search trees, but we do have that guarantee with heaps because of the fullness property. Now, are we going to be able to exploit kind of the search algorithms and insertion and deletion algorithms that we've developed with the binary search tree? No. What if you wanted to search for 65? Yeah, you don't know. Should I go left or should I go right? I don't know. It doesn't matter. It could have been hanging off of here, right? In other words, to do an arbitrary search in a heap means that you're going to do a pre-order traversal, an in-order traversal, a BFS, a post-order traversal, or something like that to find what you're looking for. So arbitrary searches are going to be linear. Right? Unfortunately, you're not going to be able to, that's not what a heap is intended for. If you want fast searches, fast inserts, and fast updates, you're looking for a balanced binary search tree. What is a heap good for, though? Right? Because of these two observations, what we can do is we can define two operations. Heaps support two basic operations. Right? One is insert, because you do, of course, have to get stuff into your heap. By the way, why is it called a heap? What does it look like? A heap. It's a pile of stuff, right? And naturally, if you were to throw something on the heap, where would it end up being? Right? If you just had a heap of balls or something, you throw it up at the top maybe, but is that where it necessarily stays? Not unless you're doing like beer pong or something like that, and you're really good at locating your shots, right? It could trickle down and fall down somewhere in the heap, right? It could fall down all the way to the bottom of the heap, right? So insert, we're going to have to be careful about that. Right? It inserts an element, it simply adds an element to the heap. The reason I gave you that visualization is because you're not necessarily adding it as a leaf. You're not necessarily adding it as at the top, at the root, right? In fact, you're just adding it, and then the heap takes care of that for you. Right? Just like your sorted list ADT that you're working on right now, you add stuff, and the list takes care of it for you. Right? And then the other one is get min or get max, depending on whether or not you have a min heap or a max heap. Right? So without going into too much detail here, how does it actually work? Let's go ahead and insert a new element here. Let me go ahead and insert, I don't know, this is a max heap now, so I'm going to go ahead and insert 101. Now before I start this animation, or I'm going to start it and then immediately pause it, you go away, right? Where did it end up? The first empty spot at the lowest level of the heap, right? If you throw something on the top, then you can get yourself into trouble because where do I put it? Where do I put 101 if I kick out 77? Okay, well, now 77's got to go somewhere. So it gets kicked out to its left child or its right child. Suppose it gets kicked out to its right child. Gets kicked out to its left child. Gets kicked out to its right child, and now you've got a gap, right? You can't predict where that gap should be. So what we're going to do is we're going to start out by ensuring that the fullness property is satisfied by inserting it at the lowest level at the next available spot all the way to the left. This is a full heap right now. Right? The fullness property is satisfied, but is the heap property satisfied? Nope. Remember, this is a max heap, so it's got to be, has to be less than its parent, and it's not. So it's easy enough to fix that. What do? Swap it with the parent. Is the heap property satisfied now? Nope. Swap it with the parent. Swap it with the parent until you get all the way to the root or the heap property is satisfied. So for example, you could, of course, get lucky and insert, I don't know, 1. Do you need to swap anything? No, we're good. Nope, we're good. Right. Or you could go halfway. Insert, I don't know, 35. Go. New child, swaps, and then you only had to do 1 swap. Right? What's the maximum number of swaps that you need to do? It's proportional to the depth. In other words, it's going to be order log n, because we've already made the observation that the depth is logarithmic. Right? Excellent. Now there are some finer points and details here on how do you actually implement this. How do I know that the left child of 3 is the next available spot? Right? There are ways to solve this and different ways of implementing a heap. You'll see, here's a hint as to what's the easiest way of implementing a heap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, what are those red numbers referring to, do you think? Indices in an array. Right? Let's go ahead and go over here and reimagine this heap. So 101, 77, 101, 77, 36, 34. It didn't have to be this big, you know. All right, dot, dot, dot. There we go. Forget about it. Now, our indices start at 1 for a good reason here. Right? How do I find the child of a node just given its index? In other words, if I have index 1 here, where's its left child? It's at 2. Remember the topology of this thing. 77 and then 36. Where's its right child? 3. Okay. Is there a pattern here? What about 5? What if the index that I'm looking at is 5? In other words, I'm looking at 63 right now. Where is its left child and where is its right child? All right. 63. There we go. 10 and 28 are its children, and that's at index 10, just a coincidence, and 11. Right? 10, 11. Do we kind of see a pattern here? In general, if it's I, where's the left child going to be? 2I. Right? Where's its right child going to be? 2I plus 1. Oops. Cool. Right? And it minus 1 if you want to really start at 0. Otherwise, it's usually presented as starting at 1 just because the math looks much, much cleaner. Otherwise, you're minusing 1 everywhere. Right? What about the parent? Can you get back to the parent? Oops. Ah. You jumped right to the solution that you need, a floor function. Why? Because sometimes it always doesn't work out, right? That if I divided by 2 here, I get perfectly 5. If I divide by 2 here, I get 5.5. Is that an index you ever heard of? Nope. So what do? You take the floor, and there. Now it's referring back to its parent. That's what you usually do, right? But floor, because we're talking math right now. Right? And of course, if you were to do this in a language that did not have integer truncation, like Python, it just becomes a floating point. PHP, JavaScript, any dynamic programming language where integer divided by an integer gives you a floating point number, you'd have to be careful. You'd have to take the floor, right? Or just take like a truncation function of some sort. Okay, cool. How do we get the max or the min if it were a min heap? It's right there, right? But I want to remove it as well. So let's go back over here. I want to get and remove the max, or the min in this case. It's right there. Right? You start at the root. You start at index 1, however you want to think about it, and you've got it. Right? Now it's gone, except that what? Yeah, I've got a gap. All right, well, I'm looking at 5 and 30. This is a min heap now. So if I want to preserve the min property, what do? I could bring up 5, right? And that will leave a gap now over here, right? I could bring up 55, and that'll leave a gap right here. Oops. But now I need to what? Bring up, oh, sorry, did I screw it up? 50, sorry. There. Now what do I bring up? 53. Gap. I got myself into some trouble here. Just like insertion, I should think about the fullness property first. Okay? So, what could I replace 1 with to ensure that the fullness property is satisfied? Yeah, let's go and think about the fullness property. Take the last available one and put it up here. Right? In other words, oops, get rid of that. And now 63 has been promoted up to be the new root. And this is now gone entirely, including the node itself. There we go. A fullness property is satisfied. Is the heap property satisfied though? Nope. So what do I need to do? Now I can do my swapping tricks. Right? 5 and 36, 5 and 50, 5 and 53, and the fullness property will be satisfied. Let's try it over here. Extract max. Right? That's get it and return it, but also remove it at the same time. 101 is gone. 30 gets promoted up. And then this is called heapification or heapify. You're fixing the heap by swapping it with children, or in the first example that we give, swapping it with parents. Okay? How do you traverse all these things? Again, it's really easy once you've got those formulas. You've got an array. You simply need to do index jumping to jump to its children, left child, its right child, or jump back to its parent. Right? Very nice. This only works with an array because of that fullness property. If we did not have that, why don't we implement a binary search tree with an array? Because you have gaps. And if you have gaps, you could have 100 nodes in your tree. If it's a skewed tree, then that means the depth is 100 or 99, right? But the size of your array to hold all that would be 2 to the 100, right? And there's no way you're fitting that in any computer. Right? So you have to be careful. Right? This trick only works because of the fullness property. Okay? Let's actually use this now to solve a problem. Right? So what I have is a data structure that I can put stuff into it efficiently. Right? Insertion, a heap insertion is going to be order log n. Right? Get max is also going to be order log n. In fact, I'm going to switch this to a min heap. Right? Is also order log n. I can put stuff in, I can take stuff out. I can take stuff out, but in a very specific manner. The minimum, right? So what if I did it over here? What if I took out the minimum, 1? Or, sorry, let's do it over here, right? Because this is the min heap. And let me get us back to square one. Oops. There we go. Let's get it back to square one here. What if I started taking things out? First of all, I took the minimum out. What would it be? 1. And then it would heapify and fix itself. Then the next minimum would be 5. It'd heapify and fix itself efficiently. Right? And again, this is going to be order log n. This is going to be order log n. Right? The next one to take this out would be what? 30? All right, 30. Dot, dot, dot. Each one of these operations is going to be log n, log n, log n, log n. Once I've taken everything out, what can you say about this sequence right here? What's the rest of the sequence? Be 40, 50, 55, 80, 60, or, sorry, now I've lost it. 53 came first. Right? And then it would be, oh, there was a 45? Sorry. 45, 53, 55, dot, dot, dot. What can you say about the resulting sequence of doing this? Oh, okay, you're already jumping to the efficiency. But what can you say about this right here? It's sorted, right? So if I insert n elements, inserting n elements is going to be order, like you observed, n times, but each one is only log n, so hand wavy version of this, n log n. Remove n elements. That's going to be also order n log n. And when you remove them, you end up with a sorted list. Add these two sequences together, and you still get order n log n. But what did you do? You put stuff in, you took stuff out, right? You let the data structure do all the heavy lifting. You let the data structure do all of the work, right? Smart data structures and dumb code are a lot better than the other way around. Right? This is dumb code. Let's look and see what it would look like. This is called Heap Sort. And regular input and output, I won't go over that, that's standard. The input is a collection, A1 through AN, of elements. The output is going to be the collection sorted. All I'm doing here is what? Initialize a minimum heap. Initialize, right? And then for each A sub I in A, H dot insert A sub I. Then what? I'll go ahead and go into a while loop here instead. Or a for loop for run it n times, right? While heap is not empty, take stuff out, right? What I'll do is I'll say I here is going to be 1, and so A sub I will end up being H dot get min, right? And then increment your I and output that collection A1 through AN. Right? Again, dumb code. Put stuff in, take stuff out. Put stuff in, take stuff out. Right? There's no that's not clever code at all. Quick sort, merge sort, insertion sort. Those are all really clever pieces of code, right? No data structures at all. You're just operating on an array, right? Here, and it's clever code because it does a bunch of recursion and fancy schmancy partitioning and then merging and zippering these things up, right? Clever code, right? That quick sort, merge sort equals clever code, dumb data structure. Dumb data structure in that it's just an array, right? There's not even any methods with an array. Merge sort, or not merge sort. This is called heap sort. Is going to be dumb code, clever data structure. Right. So that goes all the way back to, again, the theme of the course that I always conclude on. A quote by Eric S. Raymond that dumb code, or clever data structures and dumb code are a lot better than the other way around. Right? Clever code, dumb code, easy code, right? You are encapsulating all of the complexity. You are encapsulating all of the behavior into this nice reusable object called a heap, right? Once you've got that heap, you can put stuff in, you can take stuff out, and you've got these nice properties, just like a stack or a queue, right? Switching those two things around gives you, one of them gives you pre-order traversal, one of them gives you a BFS traversal of a tree, right? Clever data structures. So by the end of this course, and this is what we'll talk about on Thursday, is that one thing that you should ask yourself when you approach a problem is, well, just in Computer Science 1, what's the first question you ask yourself when you approach a problem? Yeah, is it already solved, right? Yeah, there's a function for me to do that. How do I find a substring? Oh, string dot substring, right? I'm done, right? Solved, right? Is there an off-the-shelf solution? Right? The question that you should be asking yourself after Computer Science 2 is, is there an off-the-shelf data structure that I can throw at this problem that solves it for me by just putting stuff in and taking stuff out, right? Or maybe a little bit of modifications or something like that, but what data structures would be useful in solving this problem, right? All right, any questions? We had more than enough time. I didn't think that we'd get all of that through all that, but whatever. All right, well, if you're interested, then read the full book on, it is possible to implement a heap using the node kind of structures, efficiently implement a heap using the node structures that we've already got. Basically, it comes down to the question of, if I start at the root, can I find where the gap is? Is the gap in the right subtree or is it in the left subtree? Right? And all that requires is a little bit of math. Right? And once you've got that math down, then you've got an algorithm to solve it for you. Okay, on Thursday, we will just have a course wrap-up. I don't see anything on Piazza, so thank you all 48 people for joining us live today.